Okay. It should be recording. So what he's talking about in regards to keeping in the plane of the paper is that the way the test is designed, you'll always stick with the rule. You can't flip it. So for this one, you can't pancake flip it side to side or up and down. I always think of like the block game on Cool Math Games. Ever did that? You can never do that. What you can do is rotate it. You can always rotate it because that's not moving it in the plane of paper. You're not geometrically flipping it anywhere. You're just rotating it.
Okay, yeah.
So if I were to rotate this around, all right, let's maintain our CH3s. And that's like the really big thing about the CH3s. If they're identical at the top and bottom, then if you rotate it, they're still the same. So we rotate it, this would rotate here, this would rotate here, and then vice versa for the two H's. OH, BR, H. Okay.
Okay.
So if it was completely rotated, that is acceptable. It is still the same.
More sense.
It's still the same compound, because I'm not gonna actually like look at it, but if this was R, this was S, hypothetically.
Yeah.
If you rotate it around, this would be S and this would be R, they would be meso compounds. So by the RS logic, but just rotating it is the big thing you can do. So for example, let me erase this. So you saw that I rotated it. That means that A and D should be the same.
Yeah.
Because remember, if we rotate it, well, OH goes here and BR goes here. That's where these are.
I think I had it right before I overthought
it. Yeah. And all you have to do for identifying if things are enantiomers or diastamers are looking at the R and the S configuration. Because if your configurations are, for example, if your relative, because remember, Fisher certifications are relative configurations. If your point of view or frame of reference is A, right? Let's say A again was RS. Hypothetical. I don't actually know that off the top of my head. But if B was, for example, R, there's only one difference. So that would be a diastamer. Because diastamers is if there's two or more stereocenters and one of them is different from your frame of reference.
Yeah.
However, if this one hypothetically was, let's do, okay, hold on. This one is SR. That would be the same. But if your frame of reference was B, let's ignore A completely. If it was B and you're looking at C, this would be SS, just hypothetically. If there was a complete reversal, that would be an enantiomer. Because that would mean you flipped everything or you reflected it in a mirror. So there would be a complete reversal of your configurations. So if you had, let's just break it down. You had SS, all right? If it was R, that would be an enantiomer. If it was SR, if one of them stayed the same and one changed, that'd be diastamer. And that's what you're basically doing when you're looking at these four Fisher certifications.
Okay, and then just for practice, I was trying to like number each get that S and R for like perhaps A, and I was just having trouble because it was like I don't know how to explain it, but it like the examples he went through, like it went around in a circle 1 2 3 4. Mine's going 1 2 4 3, and I don't understand like how to.
That's where you use the method. All right, if your 4 isn't in the back, you just have to flip the reversal. So R and S configuration only applies when the fourth group is in the back, in the dashed line. If it's not, you just leave it where it is and you just flip it around.
Okay.
Yeah. It's a little tough, and I think this is like the chair confirmations where that kind of stuff with your model sets really work. What I always do, here, let me bring it out. I legit came in to test 2 for this semester with 2 tetrahedrons. All right. Let me do white, blue, red. So I always assigned white as hydrogen, or like the 4th one, because your 4th group will pretty much always, most of the time, be hydrogen unless you throw something at you. So I always looked at it like this. All right, if I'm looking at this from here and my white is in the back, as long as I'm counting the correct way, I just visualize it with this simple tetrahedron. This is the most helpful thing on the planet.
Okay. Yeah, that makes sense.
Yeah. Because when I assigned the R and the S, again, the 4th group is always in the back, and I was just counted for there. If it's not in the back, well, if it's, for example, out of the page and facing me, then it's the opposite direction if I did put it in the back. And that's what I do with Fisher esterification. I just burst it around.
Could you perhaps like do the labeling for just like A, so I could see like
For A? Yeah, sure.
your like method of like going about that?
Yeah. All right. Where's my shirt? Okay.
If I'm not wrong, Br would be 1.
Right.
The carbon connected to the oxygen, hydrogen, and other carbon, like right below, would be 2.
1. That's just be 2.
And then
3,
CH3,
4.
Yeah. So that's where I was getting stuck, was looking at it from that.
Yeah, that's the thing, because this carbon has to be 2 because it's connected to that O.
Yeah.
So you always have to look at that.
So this right now would consider the 4 being pointed towards us.
Whoops.
Or the hydrogen pointing towards us.
Yeah. Hold on. Sorry, I'm trying to fix it. There's a lot of noise. So the 4 is toward us. All right. So okay. Again, let's do it normally. If it went clockwise, that's R. However, the 4th group is facing toward us. So in real life, that's going to be S.
Okay.
Yeah.
So even though it goes 1, 2, 4, 3, that still would be considered clockwise until you like flip it because the H is pointing towards us. Okay.
Yeah.
All right.
Yeah. And right now, I'm a little rusty on this stuff in general. Like right here, it would take me just a little bit because I'm not in practice yet. So that's why I'm saving it for Thursday. So before we get into that, let's just go ahead and make sure we get alkenes and alkynes. Check. Right. It's already 7:02, but if anyone has any I do have extra problem sets. I am kind of known as a dumbass among my friends and my coworkers. So you might have to remind me after the review session. Yeah. I haven't even downloaded the blank copy of the review packet yet. Let me find that. Oh. There you are. Okay. Download. Does anyone have any last minute questions? No. Sorry. Okay. I can open this. Good notes. Perfect. Yes, that's what I like to see. Perfect. Oh, phenomenal. All right, I got it to work. Problem one for problem set 7. Okay. All the ones that are achiral. Again, I'm a little rusty. For achiral, you're looking for a line of symmetry. All right. So double check. Where's my shit? There it is. Okay. So for an internal line of symmetry, that's what it means to be achiral. So you have to kind of look and just see where, draw imaginary lines. And if one makes a line of symmetry, then it's achiral. For this one, there is an internal line of symmetry. No matter how you look at it, it's symmetrical. They can, if you looked at it like from that line, you were folding it, they're the same. So this is achiral. However, if we do the opposite, let's take a look at this compound right here. If this was Br and this was on a wedge, however, this was on a dash, that would not be achiral, because obviously this is not achiral. This could be achiral, but it's not, because one BR is on the upper plane, one BR is on the opposite plane, so they're not achiral. However, for this first one, those first two are on the same plane and it's symmetrical on that line of symmetry, so it's achiral. Same kind of deal with this. All right. Obviously, there's no line of symmetry here because it's disproportionate. We have OH here, and I think that is the line of symmetry. I think I was thinking about this way. Hold on, I had that backwards. The vertical one is the line of symmetry. There's two you could look at. I'm so sorry. This first one, the horizontal one right here, this vertical one right here. The horizontal one is not correct because remember, Fisher certification, these two wedges are pointing out at you. All right. So see, this is what I'm talking about. I'm a little rusty. I've been here a while. Am I tripping? I think both are valid. But do you guys see how that's symmetrical? That's what achiral means. It means it's symmetrical. And that looks pretty symmetrical. I'll give you a better explanation tomorrow when I have time to prepare, because I prepared for the review packet, not for this quite yet.
If you want, like on the notes, it says day 15 with like chapter 4 and like the third page. I think you're right. It has like the third one with like the 4 wedges coming out, and on the left it's 2 H's, on the right it's 2 bromines. And I think you were right with the horizontal.
Yeah, okay. Because if it's horizontal, they can fold. If you look at it from that point of view, they're symmetrical in that way. Yeah, because if you're looking at it right here, I think the OH would be on the other side. For this one, Newman projections are kind of tricky, but once you get it, they're really easy. You just line them up. My reference points are usually OHs or halogens. So if there's a halogen on this, halogen on that, I just rotate it so that they're eclipsed. And if they were eclipsed, that is staggered. They were eclipsed. You guys didn't see that. Oh, come on. Technical difficulties. Okay. This is the problem with drawing on Word. I much prefer good notes. Eclipsed. The CLs would match up. This would match up to here, and then that H would match up to there. CH3, CH3, HH. There is an internal line of symmetry if you line them up in an eclipse formation. Thus, it is achiral. So this is achiral, and that's achiral. For this one, that goes back into chair conformations. I just revert it back into a cyclohexane with the dashes and wedges. So if this is axial and this is axial, they must be CH3, CH3. They must be trans to each other. Because if the CH3s were on the same plane, this would be axial, and that CH3 would be equatorial. However, it's not, it's axial. Hence, this is our compound, just looking at it straight bird's eye view into a cyclohexane. And as you can see right here, there is kind of a line of symmetry, but the branches are on different planes. So that's not achiral. The main thing that I was having trouble with is this one. If you have trouble with it, don't worry. I know it, I just know that it's symmetrical and it looks achiral. That was my logic. There's not a written explanation for it. I might ask Dr. Berg tomorrow morning. Does anyone have any last minute questions before we get into the review session? Not the review session, the review packet.
Could one be not achiral and not chiral? Just, I don't know how to explain that, but, or does it have to be chiral or achiral?
It doesn't have to be chiral or achiral. It's, if it's not achiral, you don't circle it.
Okay.
Yeah. Okay, where are you? There you are. Okay.
I have one question. I was
Sure.
confused when you were explaining the third one, like with the chlorines and stuff. Can you just go over that one more time?
Yeah, sure. Yeah. So when we're looking at Newman projections, I just rotate it around so that it's eclipsed. And I can do like some step-by-step stuff as I'm turning it. So if I were to rotate it just normal 60 degrees right here into that eclipsed, we would get an eclipse formation. Hold on. An eclipse formation of there we go. The Cl, the H, Cl in the back, that CH3, that H, and then that CH3. All right, it's not exactly what we want. Let's rotate it. Let's just go ahead and skip it. Rotate it 120 degrees because you guys know what staggered formation would look like. You guys took test 1. All right, if this is eclipse, we just move each one of these one spot over in that same eclipsed formation. So that H would go to that Cl, that Cl would go to that CH3, and that CH3 would go to that CH3. I keep drawing the staggered formation. CH3, CH3, H, H, Cl, Cl. All right, I rotate it so that it matches up. And if they do match up, everything is symmetrical, no matter which way we look at it. If our line of symmetry is right here, or with the H's, or with the Cl's, they are the same on either side. If we were to do a contrast, what if we had an eclipse formation that looked like this, for example? Right? If we had Cl, Cl, CH3, H, CH3. No, wait. Wrong one. Let's do. Yeah, okay, I know, I remember. H, H, CH3. All right, it's not symmetrical this way. Even if we line up the H's, if we were to line up the Cl's over here, the CH3 would be over here and that H would be over there, still not lined up. However, over here, each of these branches are identical, no matter what kind of line you draw in the middle of these branches. Does that make a little more sense?
Yeah, that makes sense. Thank you.
Don't be afraid to take the time to draw it out. this test is really heavy on geometrical, like spatial arrangement. I don't really have a big problem with just like imagining the image, but some people just have a lot of trouble building stuff, especially with the complex compounds he throws at you, because Fisher serification, not a serification, just Fisher structures in general are kind of ass. But as long as the more you get into biochemistry, the more I'll deal with them. All right. Let me finish cleaning that up. All right. Let me just go ahead and bring up the document. No. Can you guys see my GoodNotes screen with the test review packet?
Yeah, we can.
Great. Sweet. Okay. So the first thing we have to talk about is nomenclature. Like the first test, one of the biggest things that we'll be dealing with is nomenclature. They're going to be worth a lot of points. Yeah, it's a lot of points. It always is pretty recurring theme. Same thing with semester 2. We have more nomenclature, but you don't have to worry about that kind of nomenclature just yet. Because right now, test 1 is the big nomenclature test, because that's the big fundamentals. The same patterns for ring structure, what you start with, your priority group rules, still apply in second semester, and that's you're just adding more players basically. And here we did add more players. We added an alkene and alkyne group. If you remember that graphic I posted, you have 2 types of branches. You have a priority group, and you have just a normal branch group, right? Priority group, the moment it's there, everything else is kind of thrown out the window. The priority group must get the lowest number no matter what, even if it gives these branch group branches higher numbers. As long as the priority group gets a lower number, it's correct. Alkynes and alkenes are priority groups. So if you have an alkyne or alkene, or alkyne or alkene, they have to be the lowest number possible. However, what we dealt with before, alcohols and amines, they're higher in the priority than alkenes and alkynes. So if you have an alcohol and an alkene, the alcohol would get the priority. Same thing with amine. If you had amine, it would take a priority over an alkyne, for example. If you had both an alkene and an alkyne, they both are priority groups, but they don't really matter. They're on the same plane. If it's a tiebreaker, the alkene would take priority, but just the lowest number possible for both of them is correct. And the big ringer that I want you guys to focus on are alkenes. Right here. He will throw alkenes at you in nomenclature, and you just have to ingrain it in your head. If I see an alkene, it has to have E or Z. All right. If you miss that, that's an entire 1 or 2 points off. Especially in future problem sets, you have to have the E or the Z confirmation. The main exceptions are cyclic compounds, because if they're cyclic, they're pretty much always going to be cis to each other, because it has to point inward to close that ring. I think you have to have ring structures of 16 or 18 carbons before you have trans alkenes in the ring structure, which is something you don't have to worry about. So ring structures, you're fine, but if you see an alkene, you have to name it. One of the exceptions are structures like this right here. This doesn't tell you anything. These H's right here could be top or bottom. You can't really tell because that's just how it's written. So you don't, for these kinds of compounds, you don't really have to put E or Z. But for Kukulay structures like this, kind of shows you have to show E or Z. Any questions regarding that before we go over E or Z? I'm going to take the silence as a yes. Now, for me, I use the alphabet trick for both E and Z conformations as well as alkyne reactions, the alphabet, right? So at the very beginning and at the very end, all right, you have A, B, C, cis. And at the very end of the alphabet, you have Z. So at the ends of the alphabet, C and Z are paired. And on the inner sides, you have D, E. And then somewhere in here, you have T for trans. So on the inner side of the alphabet, we have E and T. That's how I remember it. C and Z are at the very end. E and T are on the inner parts. Mainly, I just remember C and Z are at the end because I can kind of put together E and T from process of elimination. Because there's only two pairs you really have to know. But C and Z are the main things you have to know. And that's how you put it together. Priority groups for denominating which side of that alkene applies for your stereochemistry goes to the highest atomic weight group. All right, so straight up, you have a bridgehead carbon and a bridgehead carbon. Whatever compound they're attached to, that's where you decide. So you decide by the highest atomic number. For this pair right here, F versus C, fluorine's a lot bigger. So fluorine gets priority. For this pair right here, O versus C, O is a lot bigger, so O gets priority. If these are on the same side, what is the conformation? Open up chat. You guys, let me open up chat. You guys can throw answers in the chat as well if you want. Yeah, it's Z. Because these are cis to each other. They're cis, C, at the other end of the alphabet, Z. They're Z. So yes, Mia, you're correct. Again, let's take a look at it right here. You have a bridgehead carbon and a bridgehead carbon. All right. So let's look at whatever compound they're directly connected to. This is a problem that you will see. They're all connected to C's. Well, let's take a look at what the C's are connected to, because you have to look at the next layer over to the side. All right. So this has a CO bond and a CO bond. O has a CC bond, C. These three numbers, these three letters are what it's bonded to. I put two O's because it's bonded to oxygen twice. For this C right here, it's bonded to an O for that OH, and then an H, and then an H. All right, it's bonded to two hydrogens and then one O in that OH. Now let's compare them. This one has two O's, this one only has one O. So this carbon gets priority. Now let's look at this one. You have C and C. Let's move on to the next layer. We have a C connected to both two H's and then another C to continue on that chain. So we have a C, H, H. For this one, we have two hydrogens. However, we have a Br, so we have a Br, H, H. So which one will get priority? It would be this bottom C. They are trans to each other. So what denomination will we put? What letter? Excuse me.
E.
E, yeah. 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 Let's go ahead and jump into nomenclature. So we already said that this alkene right here cannot be interpreted. So we don't need to worry about C or Z. However, we can still worry about the other things. Let's go ahead and just first off identify the parent chain. We have 1, 2, 3, 4, 5, 6, 7, 8, 9. It's a nonane. If we number it either way, 1, 2, 3, 4, 5, 6, 7, 8, 9. 1, 2, 3, 4, 5, 6, 7, 8, 9. Which one gives us the lowest confirmation? Or not confirmation, the lowest number set would be this one, because we were looking for the lowest numbers for that alkene. So 4 and 5 definitely beat 5 and 6. So we want this one. It'll be a non-4-ene. And now we just need our branches. So if we were to number them, we have an 8 bromo and a 3 chloro. Let's put them alphabetically. 8 bromo, 3 chloro, nonane, and that's your compound. Don't forget, you have to order them in alphabetical order. And between numbers and letters, you need dashes. And between numbers, you need commas. So if you had like a 3,3 dichloro, for example, right? Two numbers next to each other, you always put that comma. A letter and a number together, you always put a dash. And that's why for here, when we connect it with that parent chain, letter to letter, you don't need anything. So I had some people on the test leave out or accidentally put in a dash. The main thing was right here. Good amount of people put dashes there. It's not what we're supposed to do. All right, let's move on to this one right here. Now we do have an alkene, but hopefully that rings something in your head like, all right, we need C or Z. Not C, E or Z. But it's cyclohexane, so we don't really hexene, but we don't really need any stereochemistry denomination because it's always just going to be cis. To number it, we have to use our cyclic naming rules. Your first carbon always has to be on one of these priority groups. And what's a priority group in this compound? Well, that's the alkene. So your bridgehead carbons have to be 1. So you have to start either from here or right here. Either one of them you can start at. But wherever you start, you have to cross that bridge in order to count it. So you can't number this 1 and then go 2, 3, 4. You have to cross that bridge. All right. So if we were to start here, all right, this would be 1, 2, 3, 4, 5, 6. If we were to start here, we'd have 1, 2, 3, 4, 5, 6. We have a 1, 2, 3, not 2, 1, 3, 4, 6 versus a 1, 3, 5, 6. There's a difference here. We want the one with the 4, 6. So we want to go clockwise. Thus, if we went that way, we went with our black numbering system. We would have 4 bromo. We have a propyl group, methyl group. Methyl group would go before propyl. So we will have 6 methyl. 3 propyl. I'm going to put ... here. That's supposed to be no space, but propyl, cyclo, hex, 1, ene. Does that make sense? Anyone have any comments, questions, concerns? Now let's look onto this cyclo butadiene. Well, I just told you the answer. This is a diene, cyclic compound, has an alkene. What's the priority group? There's no OH, there's no amine group. So your priority group is going to be that alkene group. So your bridgehead carbon, you might think you can start at any one of those cyclic carbons, but the thing is you have to start at either one of these carbons, these two right here. The reason being is that they're branches. So if you have a butadiene, that's guaranteed to be 1, 3, no matter which direction you go, 1, 3, you're gonna want to start at a carbon that already has a branch on that first carbon. So you have to start at these. A big mistake I saw was one of these, CH3, CH3, Br, Cl. A lot of people started here and went this way because, you know, the first point of difference, you're correct. But the first point of difference is actually right here. That's the first point of difference because you have a 1, either direction you go. Well, you already have another branch on that same carbon. So your starting point has to be the one with the most branches on it. Something we kind of glossed over. I didn't think you'd throw that at the test, but fortunately, it was on the test, but it goes by the same logic of the first point of difference. The first point of difference, you always start at the one with the most branches, assuming that that carbon has a priority group. Because again, priority groups have to have that first, the lowest numbers possible. So if we were to start, well, at either of them, we would get the same numbers, 1 and 3. The tiebreakers are going to be alphabet. What's the alphabetical preference for an E versus an M? E in ethyl, M in methyl, it's going to be the E. So we're going to start at the ethyl group. So this is 1. Remember, we have to cross the bridge. 2, 3, 4. So we have a 1 ethyl, 3 methyl, cyclo, buta, 1, 3, diene. That's our compound. I want to double check, make sure I'm recording. Am I recording?
Yeah, I think so.
I am? Okay, perfect. Okay, my heart almost just dropped. Okay, cool. All right, can you guys still see my screen again?
Yeah.
Great. Okay. Now we have a Kukulay structure with an alkene. However, ding, 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 it's an alkene. You have to have C or Z labeling. It's not a cyclic compound. What kind of conformation would we put this? E or Z? Let me pull up chat. You guys can throw it out in chat as well.
E.
It would be E. As they're trans to each other. If there's a bridgehead carbon, there's a bridgehead carbon, you have a Br and a C. If you're comparing them to H's, they obviously take priority. So this is trans. So this would be E. And E, you just leave it at the beginning and then you don't fuck with it. And then boom, you're right. Might be thinking, is it that easy? Yes, it is that easy. Just put it at the beginning and then you leave it alone. With the E out of the way, let's number it. So we have a 1, 2, 3, 4 butene. And right here we have 2 priority groups, an alcohol and an alkene. The alcohol would take priority. So even though you might want to count this way, 1, 2, 3, 4, you have to count this way and give alcohol the 2. 1, 2, 3, 4. So we would have, well, bromine's on 4 bromo. But 3 ene 2 all. There's only 1 alcohol. There's no diol or anything. So we have to drop the E in butene.
Can you explain
Now
why
it's-
it's trans real quick
What's that?
again? Can you explain why it's trans real quick again?
Sure. So the big ringer is the alkene. You have to look at the bridgehead carbons of that alkene, and then you look from there. If there's nothing there, it's implied, obviously, that those are H's. They're H's. Well, if you're comparing a Br to an H and a carbon to an H, that carbon will obviously take priority, and that Br would take priority, and they're trans to each other. If, for example, let's just toss it out. What if this was an OH? Ooh, that was an OH. It would be cis because you have a carbon being compared to an oxygen. The oxygen would take priority. But alas, there's nothing there. So we assume it's just an H. Does that answer your question?
Yeah, thank you.
Ooh. All right. Let's look at this compound. This one is a jiffy. Let's just find the longest parent chain real quick. That's going to be this one. Because if we went here and went down here, well, that's only 2 carbons compared to 3. We want to go up. Same thing here. This is only a methyl group, and this is an ethyl group. We want to go with this one. So this is our parent chain. Our parent chain is a heptane, 7. Let's number it. 1, 2, 3, 4, 5, 6, 7. 1, 2. Let me use a different color. 1, 2, 3, 4, 5, 6, 7. All right. Which numbering would be correct? Black or pink?
Pink.
Pink. Because even though an alkene is there, you have two priority groups, an alkene and an amine. And the amine would take priority over an alkene. That's something you will have to know. I think for semester 2, we throw carboxylic acid derivatives, and we have to know that priority, carboxylic acids, then esters, sulfonic acids, all that funky shit. Whatever, I digress. So the pink numbering is correct. So we have an 4 ethyl group, 5 methyl group. We have a 7 chloro group. So C, E, then M. So just do 7 chloro, 4 ethyl, 5 methyl, 1 methyl, hept. You gotta start that first bridgehead, 4 ene, and there's only 1 amine. That's at 2. 2 amine. We drop that E because there's no diamine or dial. There's only 1 amine. And this is missing something. What do we add?
E or Z.
Yeah. What letter would we add? And this is one of the tricky ones, because right here, all right, if our alkenes right here, all right, let's look at our bridgehead carbons. Carbon, carbon. It's attached to a carbon, 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 carbon. There's a tie. So we have to look at the next layer and look at what it's connected to. Well, right here, there's 2 H's and then a carbon. This is connected to 2 H's and then a carbon. Well, that sucks. However, even though that these are the same, this branch is a lot bigger because it has that amine group. So if we were to expand it, there's 1 H, a carbon, and a nitrogen. This one is only attached to 3 carbons, 3 hydrogens, my bad, 3 hydrogens. So even though there's what, 1, 2 extra layers you have to look at, which one's heavier? It's going to be this side. Is that making sense for people? I don't want to assume. Is everyone good on that? Okay. I'm going to take the silence as yes. Now working on this left side, let's look at what it's connected to. Hydrogen, 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 hydrogen. So this is connected to a carbon, hydrogen, hydrogen. And this one is connected to a hydrogen, hydrogen, hydrogen. Out of these, which one takes priority? It's the one with the most carbons. All right. So one with most carbons, this side is a lot heavier. If they're on the same side, they're cis. They're cis. What letter do we put?
Z.
Z. Yeah. And personally, I write out what letters are attached to. For example, for this one, and if you're comparing these carbons, for example, let's say this was connected to another carbon, and this is connected to what? 2 more carbons, right? There's a carbon right there, and then there's a hydrogen right there. If I were to write it out, again, this is hypothetical. This is connected to a carbon, carbon, hydrogen, carbon, carbon, carbon. I always write out whatever they're attached to, cross off what's symmetrical, and then I pick which ones are different and which ones heavier. That's what I do. It's something I highly suggest you do. I can't really show it on this example specifically, but hopefully we can see it later. Now right here, we have a cyclic compound, 2 priority groups, and one of the priority groups comes in twice. So I have to put a di prefix on that suffix. So it's a little bit tricky. However, if we stick to our rules and what we know about cyclic compounds, what has to be the first carbon?
The alcohol.
Yep. the one connected to the alcohol has to be the first carbon. That's the rules we've been going with, because alcohols take priority over alkenes. And the great thing about this one is no matter which way you go, the alkenes have the same numbers. So going this way, 1, 2, 3, 4. The other way, 1, 2, 3, 4. 1 and 4, 1 and 4. So it's going to be 1,4-diene no matter which way you go. So it would be cyclo, hex, hexadiene, hexadiene, yes, hexa. 1. Did I say 1? I meant 2, 5, not 1, 4. I'm so sorry. Because this is 1. I bet you guys were looking like, what? I'm so sorry. All right, this is 1, 2, 3, 4, 5, 6. Okay, 1, 2, 3, 4, 5, 6. I thought something was wrong. 2 and 5. Again, the first ridge hydrocarbon, your numbering comes across 2 and 5. Still symmetrical, but those are our numbers. 2 and 5. 2, 5, diene. Drop that E because we have an all. 1, all. Does anyone have any questions regarding that? This is a little bit of a toughie. Is everyone good? All right. If you guys are good for me to move on, I'm going to digress a little bit and talk about the main concepts for reactions. So if you weren't here for the review session, the office hours from Sunday, the big reactions you have to know the mechanisms for, like where the electrons are going, what bonds are forming, the rate determining step, where you just write RDS over the arrow. That's all you have to do. But the ones you have to know in specific are HBr, H2O, H2SO4, and then solvation, which is any kind of ether. So not ether, alcohol, CH3OH, H2SO4. Those are 3 types of reactions you'll see. And this can always be like CH3, CH2OH, just any kind of alcohol in general. That's solvation. So you can add an ethyl group, propyl, or ethoxy, propoxy group on it. But these are the main 3 reactions you have to know step by step. And the thing is, all 3 of them can undergo shift. All right, so you can have a hydride shift and a methyl shift. And if you can remember from what we talked about on Sunday, shift happens wherever there's a carbocation. So if there's a carbocation intermediate, shift happens. Because if you have a carbocation on like a secondary carbon and there's a tertiary carbon right next to it, it's going to hyperconjugate and send some stuff over so it stabilizes it, because secondary carbocations, if you remember, if you read the textbook, are not stable at all. But tertiary carbocations, relatively stable. So that's what we like to see. So these are the main 3 reactions you see. And if you were ever just writing reactions like this, where you're predicting the product, those 3 will always have shifts if it can happen. Something I would like to note, let's say if you had something like this. Yeah, an alkene that looked like this. Obviously, if you were to add an HBr right here, the H would add on this one, and this carbocation where the Br would hypothetically add would be here. However, right there, it's already tertiary. I know it's really small. Let me zoom in. That's already tertiary where it's adding. And some people might be thinking, well, what if it's a carbocation, I can do a methyl shift because there's a methyl group right there. However, if wherever that carbocation is, if it's already on a tertiary carbon, it won't shift, because again, tertiary carbons are already stable enough. Because if you do a methyl shift or a hydride shift, you're probably transitioning it to another tertiary carbon, which is unnecessary. If not, you'd be transferring it to a secondary or primary carbon, which is even worse. So if it's on a tertiary carbon, it's where it wants to be and it will not shift. Is that making sense for you guys? That's something I saw, I think, on problem set 5. But shift happens, there's a carbocation, and the 3 big ones you have to know all have carbocation intermediates and thus can shift. The bulk of the reactions you guys have to know do not have carbocation intermediates like syn addition or concerted reactions, and you don't really see shifts very often. The one shift I did leave out other than hydride and methyl shift are ring expansions. And remember, that only really happens if you have a cyclobutane or below. If you have a cyclopentane or cyclohexane, it's pretty stable. Like the torsional strain or angle strain, not enough to cause a shift, not quite like cyclobutanes and below. Not something you really see. All right. So with that out of the way, let's go ahead and just work on these reactions. So there's a big difference between a reaction that looks like this and a reaction that looks like this. Can someone tell me what the difference is? One is protic. Can someone tell me what the difference is? Did someone say it? I think someone said it. The right one is protic. This is protic. So it can add an OH because OHs are pretty nucleophilic. This is protic. It can release or donate hydrogens. Protic is also nucleophilic. It has a lone pair on that oxygen, and it can attack whatever underside you have. I think it's a better idea to just play it out and take a look at what we're looking at. We know that the Cl2, Cl, will react with that alkene. Alkene would attack here, and the electrons would go there. So our intermediate would look something quite like this. Now, this is a very unstable intermediate, but it just exists for a moment. And what that looks like in a better, let's do a Hayworth structure. What that would look like would be something like this. All right. This side would be completely empty. Thus, any kind of nucleophile would be perfect to add. So for a solvent with CH2Cl2, there's no nucleophile there. There's no lone pairs on that central atom that will attack there. However, you have an H2 on this one where you have an O with lone pairs on that oxygen. It's protic. You can have it as an OH, but more realistically just H2O. That can attack that, or you can have Cl attack from under there. Those are two very viable nucleophiles that add from under whatever alkene or what was an alkene. Yeah. So this one, the only nucleophile present is Cl. However, for this reaction, you have two nucleophiles present, H2O and Cl. Which one's a better nucleophile? I'm pretty sure it's just going to be water. That's how I remember it. That's, yeah. Yeah. I don't really know if I have anything else to say about that. Do you guys have any questions regarding this? Obviously, going back to this reaction right here, there's no H2O, so the only nucleophile present is that chloride ion. So if you had something like this, the only thing that would add from the underside would be chlorine. So you would have something like this. Yeah. Does anyone have any questions? That's the science behind it. But all you really have to know, all right, Cl2H2O. This one adds, not B, whatever alkene you have, it adds 2 halogens. This one adds a halogen and an OH. The OH being the most substituted. If you're writing flashcards, that's all you have to write for it. And that's kind of all you need to know. There's no work around it. Here's one of the reactions where you do have to know what's going on for each step and like possibly write it out. Right here we have an alkene. And this is one of the reactions. Well, ding ding, we have a carbocation intermediate, so shift can happen. However, if you guys remember, this adds an OH and an H. It basically splits up the water. That's how I see it. If you remember right here, it would add here, the H and the OH, but there would be carbocation. So the H would be right here, and the carbocation would be right here. Even though shift can happen, this is already tertiary, so shift doesn't need to happen. So it's perfectly content with where that carbocation is, and that OH will just add right there. So our product would be OH, H. That's it. That's all I have to write. For this one, HBr, well, we add an H and a Br across the alkene. However, this, again, one of the reactions you have to know step by step, and is a carbocation intermediate, so shift can happen. You have a primary and a secondary. Well, you have a secondary carbon that's not quite tertiary, so shift can happen. And shift does happen. What does the carbon adjacent to it, what can it donate? Hydride or methyl group? It's going to be a methyl group. So if we were to have the intermediate of, let's say it was CH3CH2, CH3CH3, the carbocation intermediate would be right here. CH2, and then that H right there. That'd be the intermediate. This would shift over there, and that carbocation would thus move. Let me redraw it once it shifts. CH3, and now the carbocation is right there. It just basically trades places when it shifts. That's a very stable tertiary carbocation, and now the Br can attach there. Attack there, and our final product would be this. Does that make sense on when and where shift can happen? Does anyone have any questions regarding carbocations, shifting in general, or what we've covered so far? The silence means, what's up?
Sorry, I had a quick question. So basically what happens here is, because it would be more stable in the tertiary carbon, the methyl group that's already there would just have to switch, like basically swap over to the secondary, so the bromine can go there.
Yep.
The tertiary. Okay, cool. Thank you.
And the bromine or whatever nucleophile you have will go wherever the carbocation goes. It's just basically a placeholder.
Okay, thank you.
Now, boration is an anti-Markovnikov addition of H2O, or basically an OH and an H. So it's pretty much the same thing as hydration, H2O, H2SO4. However, that adds to Markovnikov because that has a carbocation intermediate, and it has to be on the most substituted carbon, thus Markovnikov. However, boration is anti-Markovnikov addition. So if we were to add the alkene, you have a tertiary and a secondary. Boration adds an H and an OH. Excuse me. This anti-mark, the OH has to be on the least substituted carbon. So it would go here. If we were to write it out, so CH2, CH3, this, let's do a wedge. And it has to be anti-addition. Wedge. So the OH added on one plane, the H added on the opposite plane. And it doesn't have to be wedges. The ethyl group and the OH can be dashed and the H being wedged, as long as like relatively they are correct. Just the fact that you show that they're anti-addition is fine. You're also welcome to just leave them as lines and write anti-addition or write trans opposite plane. That tells us you know what's going on, and we will give, or I'll give you credit, but I'm pretty sure we'll give you credit for that. All right. O's analysis is probably the easiest thing to remember, because all you have to do is cut across the alkene. So whatever was there, you just make them ketones. You just basically plug them up with oxygens. And if you write it like that, that's perfectly acceptable. You're done. Yeah, that's kind of it. Does anyone have any questions regarding that? Pretty simple. The mechanism is
That easy?
yes, it is that easy. The mechanism is so super complicated, and you don't have to know it at all. All you have to know is what it does.
Okay.
Yeah, you just cut across the alkene. For example, let's do something like this. Sorry. All right, stop hacking. That's my cat. I'm sorry. Get out of here. Okay. You just cut across the alkene and you just plug it up and form these compounds. That's it. If they're not connected in a ring, you have two types of compounds. Let's do it again. If you had a compound that's like this, like that, you cut across that alkene. Those are the two products you'll have. You just cut across the alkene. That's it. It's that easy. I don't know why I erased that cyclo. Oops. All right, I'm gonna leave that there. All right, HCl. Again, one of the reactions you have to know, there is a carbocation intermediate. We have a secondary, we have a primary. Hopefully that rings something in your head. We have secondary alkene that can add something to a carbocation. However, the carbocation would be on that secondary most substituted carbon. A secondary, not quite tertiary, there's a carbocation intermediate. So what will happen? Shift will happen. This carbon cannot donate methyl or ethyl groups because they're in a ring structure, but it has a hydrogen that it has. And that hydrogen, kind of like if it was a methyl group, would just trade places with that carbocation. So your new intermediate after the shift would look something like this. I don't know why my pentagons are so ugly, but your new intermediate would look something like this. H, that was your original CH2 right there. This is your H again. That's what your intermediate would look like. And wherever that carbocation goes, that's where the nucleophile goes. And your nucleophile is that, the most electronegative portion of your reagent. All right, and that'll attack right there. So your final product would be Cl and an ethyl group. Does anyone have any questions regarding that? Great. This is one of your last reactions, solvation. Again, one of the reactions you have to know step by step. There is a carbocation intermediate because solvation and hydration right here, the mechanisms are exactly the same, except H2O is just replaced with CH3OH. There's nothing different about these two. So that's a big plus. So you kind of really have to just memorize two mechanisms. But going back to this reaction, there's a carbocation intermediate, and let's look at the alkene. We have a secondary. The carbocation can add on either one of those secondary carbons, but shift can happen. However, if we look at the adjacent carbons, they're primary. I don't know why I wrote 0. they're primary. So if they were to trade a hydride or a hydrogen group, it would be on a less substituted carbon. So the carbocation is like, you know what? I think I'm cool right here. So they'd much prefer secondary over primary. So it would stay where the fuck it is. And thankfully it's symmetrical. Let's just say it's right there. Let's add that H right there. Yeah, and CH3. And whatever nucleophile you had, it was CH3OH. It would add on to that carbocation. And then another alcohol would take that hydrogen away. And that is the compound we would have. Does anyone have any questions regarding this reaction in particular? Because we don't see a shift. And this reaction, hopefully you guys know, just adds whatever group you have attached to that H. Any questions? Oh no. Among Us. Have you guys heard of the hit game Among Us? I'm sorry, I had to. Okay.
You absolutely did not.
Sorry.
Bruh. I'm falling asleep and I just hear Among Us and I get shot back awake. Like, what the fuck?
Okay. Yeah, my roommate, whenever she's drunk, I always like coerce her, like, please, for the love of God, say Among Us. It's really funny. Okay. I'm assuming we don't have any questions. I think fall semester last year, someone made an Among Us joke in OChem. I forgot what it was about, but it was kind of funny. Okay. Let's move on to the mechanism. Thankfully, we're going to move on to the hardest mechanism because of how much volume there is, the solvation reaction. Again, this would be the same thing as if it was H2O or HOH, because again, you have an alcohol group right here. In the second semester, you kind of imagine OH more as just an OH alcohol group, but connected to an H. It's a weird way to look at it, but it kind of draws a lot of similarities because if you get into semester 2, water and alcohols have a lot of similar properties because the main difference is water has an H, but an alcohol has an alkyl group, but they still have that alcohol. Did I say alcohol group? Alcohols have an alkyl group attached to the alcohol, but both still have OHs that are very nucleophilic or protic or basic. It's a very magical functional group. Very magical. However, I digress. Let's go ahead and make this oxonium ion. So if he were to give this to you in a test, he would split it up for you. He would first ask you to make the oxonium ion. And the oxonium ion is always something where you have an R, O, H, H, where you have a positive formal charge on that H. It's basically a protonated alcohol group. So a good example of oxonium ion is maybe like a hydronium ion. Same thing as an oxonium, but hydronium, instead of that R, has an H. Kind of get where I'm going? That's the oxonium ion you're kind of looking at. So the formation of something like this, what we want is, well, what is our R group? That's our alkyl group from that alcohol. Right there. That's what we want. So let's add it. So we have a CH3, CHOH. We have HOSO. It is a very good idea to know the structure of sulfuric acid because you will have to draw it out. You don't have to know the structure of nitric acid just yet, and you will never have to know the structure of perchloric acid. So just know sulfuric acid and you should be good. Right here, that lone pair would attack that hydrogen. That lone pair would go back there. So what you would have left is going to be, don't forget formal charges. You have to write formal charges everywhere. Wherever there's the formal charge, you have to write it. And then you would have CH3, it's supposed to be 3, CH2, O, not O. There we go. That's our oxonium ion. And there are two products. These are counterions. You have to include both. But that's the formation of the oxonium ion. The same kind of deal adds here. All right. Well, if we had this is our alkene. Pretty sure. 1, 2, 3. Nope. 1, 2. There we go. That's our alkene. This right here, that's primary. This one is tertiary. I'm going to keep that in mind. So tertiary, primary. Well, if we have this oxonium ion right here, H plus, this double bond will attack that H. That lone pair will go down here. So we would have a reaction. They would produce, what is it? Carbocation here, and then the H. Because remember, the H would always go to the least substituted ion because it wants the carbocation to be on the most substituted. Then you would have just a floating OH, whatever you had. And so the big thing you always have to write is the rate determining step. And that's always the formation of the carbocation. So that's something you can write down because it is something that is pretty consistent with semester 2. The rate determining step for any mechanism is 9 times out of 10 the formation of the carbocation. And again, the 3 reactions you have to memorize, all of them form carbocations, all of them can shift, but the main thing is the carbocation. So this step right here, that's the rate determining step. So now that we have these intermediates, again, they're intermediates, we have a floating, look at it, alcohol. And alcohols make good nucleophiles. So they would add right there. So I'm going to keep that H there just to stay consistent. This is that methyl group that was there earlier, but I'm just bringing the alcohol down just that I have more room. And again, we have another ion right here. That's a methyl group, no, not methyl, ethyl group. I put the plus twice, my bad. Now you might be thinking, how do I make this into an ethoxy group? How do I get rid of that H? Well, you have another OH right here, just floating around in the solution. And if you take lab, the thing you do for this is that you add excess alcohol so that they can act as bases and basically take away that hydrogen. For this step in particular, something that is perfectly acceptable is writing B and then a lone pair, because that is any convenient base. And that B represents a Lewis base, because a Lewis base always has a lone pair. It's willing to give up and just basically take away a hydrogen. So that whatever convenient base you have right there. Personally, I use convenient bases just because it's a lot easier. Take the hydrogen, then the electrons would go back there, and then finally you would have CH3, CH2, C, our ethoxy group with that H taken off, CH2, that original H that was there, CH3. And note, there's no shift happening, no hydrogen, because whatever that carbocation added, it's already on a tertiary carbon, so it doesn't need a shift. All right. I think the last thing we can probably knock out. Let's save alkene and alkyne nomenclature for Thursday. Let's go ahead and try knocking out these reactions. All right. Okay. So this right here is boration. And boration and mercuration are they're very similar because they convert alkynes into a carbonyl group. So whatever alkyne triple bond you have will form, that's supposed to be an oxygen, a carbonyl group. But the difference is boration can only produce an aldehyde. So boration can only produce an aldehyde. And that's where you have an R and a terminal carbonyl, where it's attached to a hydrogen. Mercuration, it can form both aldehydes and ketones, but it mainly forms ketones because it has to have very specific conditions to form an aldehyde. So for test 2, just know mercuration forms ketones, internal carbonyls, R, C, double bond O, R. And the way I remember this, like I said at the beginning of the review session, I use the alphabet. Boration and aldehyde are at the very end of the alphabet, and they're right next to each other, A and B. Mercuration and ketones are on the inside of the alphabet, and they're relatively next to each other, M and K. Mercuration, ketone, boration, aldehyde. That's how I remember it. I just use the alphabet because I know the alphabet. I hope you guys know the alphabet. You're welcome to sing the alphabet while you're taking the test. Yeah. All right. So right here we have a terminal carbon and we have an internal carbon for that alkyne. Where would that carbonyl form? You guys can throw it in the chat. Terminal or internal?
Would it be terminal?
Yep. And you guys did very well on this problem set. It's pretty solid. So H, C, C, that other H added there. H, CH2, CH2, 1, 2, 3, 4, 5, 1, 2, 3, 4, 5. 5 carbons. That's what we have. We would have an aldehyde. All right. And right here, we have 2. Let me change my colors again. We have 2 internal ones. All right. And we have mercuration. Mercuration, well, they turn things into ketones. So if it was a terminal and an internal, it would react with the internal carbon. However, both are internal. So it would react with both. How many products would we get? We get 2. CH2, CH2, CH3, CH3. I'm just writing it twice. CH2, CH3. So you can either have a ketone right here, H, H, or a ketone right here, H, H. You can have either one of those being products. Now this one's a little tough. I don't think you guys really went over this quite yet. The mechanism I'm not too confident in, but what I do know is that all you have to do is just memorize what comes out of it. A lot of these, you just have to memorize what comes out of it. Like what is it? Like your Br2H2O or your Br2 CH2Cl, like your halogenation, halohydrogenation. You kind of really just have to know what comes out of it. Lab, you have to know the mechanism, I think. But for this one, you just have to know what comes out of it. And for this one, I'll just tell you, there's not much to talk about. You get a ketone and a halogenation. It's kind of it. You have water. It'll more likely just want to be on that internal side. It would prefer that ketone. So yeah, that carbon oxygen bond wants to be on a more substituted carbon. Yeah. Anyone have any questions regarding this? There's not much you have to know about it. You just, once you see it, just know how to change your reaction and just what to add across the alkyne.
When we're drawing the products, do we need to write the lone pairs? Because I did, but I didn't know if we had to.
Now,
No.
the lone pairs, you mainly only have to draw for your mechanism because the mechanism actually has to deal with the movement of electrons. So we have to see all of them. But when it comes to this stuff, nah, you don't. It's kind of implied too. For this, that is. I don't think any of the reactions we have for you guys right now have formal charges in the final product. So I think you're also good on that. Did that answer your question?
Yeah, thank you.
Yeah, of course. Now, HCl in excess, that basically means we have excess HCl and we can assume that we have enough for two halohydrogenations. There are two products in this because, again, across the alkyne, they're both internal and internal. They're both secondary carbons. So the Cl or whatever that nucleophile is adding to doesn't really have a preference. So it would be CH3, CH2, C, CH3, CH2, C, CH3. You have two Cls adding here, H, or the other way around, H, Cl, Cl. I'm pretty sure like 95% of you guys got that right on the problem set. So I'm assuming you guys don't have any questions on this. Unless you do, voice them now, but you guys did pretty solid on this. Great. Now, H2 Lindlar's catalyst is something super, super handy to know. It's something that will come up test 3 in the final and semester 2 when you do your synthesis stuff. It is very handy, something super helpful. The thing to note about this is that it basically, for your alkyne, it just adds hydrogens across without making that alkyne into an alkane. It just keeps it as an alkene. It just reduces it down halfway. So that's why Lindlar's catalyst is super helpful. However, Lindlar's is syn addition. So if we were to have our alkene that it reduces it down to, all right, where should we put our H's? Cis or trans?
Cis.
Yeah. Syn addition. Sus? No, I'm joking. Cis. Sorry. I had to. H, CH3, CH3. That's all you have to do. Now for this one, this is anti-addition or trans addition of the hydrogen. So it's the kind of similar, it's Lindlar's catalyst cousin. This is something pretty tough. Straight up, just memorize it. Either being like really short-term memory, you can memorize it the night prior or the morning of, and then completely throw it out of your head at the end of the day and save it again for the final. You're welcome to do that. This one is a little bit of a toughie, just Na and H3, just any kind of lithium and then ammonia. So like Na or, did I say lithium? Any kind of alkali metal, so like sodium or lithium or potassium and ammonia, and then really cold temperatures. This is a pretty big toughie. I'm pretty sure, I don't know where the lithium is, but you can use Na or lithium. Lithium is another really popular one. Lithium is very reactive as well. All right, here we have mercuration. However, we have a terminal and internal. Where would the mercuration add to? You guys can throw in the chat as well. Internal or terminal. Mercuration M was also in the middle of the alphabet. It's going to be a ketone. So it's going to choose that internal one. What's going on? Add here, and then H is right here. That's it. Set of reagents that allows for a syn addition of H2O, not H2O, H2. That would be this one. This is anti-addition, and this is complete addition. There's no syn addition or anti-addition because it just adds things twice. And when that happens, it all turns it into sigma bonds. So that doesn't really matter. For the anti-addition, we talked about this: sodium or lithium, ammonia, and then really cold temperatures. So I don't have any last minute questions regarding this before we finish up. The rest of this, I'm gonna go over this lightly again at the beginning of Thursday, mainly the carbocation rules, shifting, the mechanism, and then we'll get into nomenclature and then chirality, which is a whole lot of fun. But if you don't have any other questions, you guys are welcome to go now. I'm going to stick around if you guys have any last minute questions for problem set 7. I will have office hours tomorrow at 1, but it might be short because I'm probably going to take that time to prepare for your review session Thursday. But yeah, you guys are welcome to go ask about problem set 7, and then that's it. You're welcome.
Real quick,
Yo, what's up?
could you go back and it was that one thing you were doing with the trick to remembering the priority, like with the ABCs or whatever.
Priority like E and Z?
Yeah, yeah, like that.
Sure.
What was that again?
The E and Z, kind of similar. You were screen. Can you see the screen right here?
Yeah.
It's kind of similar to mercuration and boration, but let me just redraw it. For my trick to remembering C, Z, and then trans E is the alphabet. So you have the beginning of the alphabet A, B, C, and at the very end of the alphabet Z.
Okay.
They're at the very beginning, at the very end of the alphabet. So I automatically just link them together because they're at the very beginning, at the very end. And on the inside of the alphabet, we have E, this is for cis, by the way, and then we have T, this is for trans. That's what I have. Something that Dr. Burke also uses is this. Cis is the same side, and that uses, you can use it as Z. But if you're more into mnemonics, that's also super helpful. But personally, I like to use the alphabet just because it makes a lot more sense to me what I pair. Like if I know C and Z are paired, then E and T have to be paired because they're the opposite pair. They're what's left.
Okay, gotcha.
Yeah. So as long as I know C and Z are paired, I can pretty much assume E and T.
All right. Well, thanks.
Of course.
I might send you some emails because this is a tough chapter, you know.
It is pretty tough.
Yeah. So I'll see you around.
Of course. See ya.
Bye.
See ya.